Here is a video on mixed Nash-Equilibria and normal form games.
So far, in normal form games, we have only considered pure strategies. Some games, however, have no Nash-Equilibria and pure strategies. These are usually games that, if one player knew the pure strategy of the other player, that player would always win. As a result, there is no stable system. For example, rock, paper, scissors is such a game. As we can see by looking at the best responses, there is no Nash-Equilibrium in pure strategies. Now think about how you would play several rounds of rock, paper, scissors with a friend. What would you do? You would probably try to do these two things. You try to figure out which strategy your friend is playing. So maybe they never play the same move twice in a row, or they play whatever move would have won the previous round, or whatever other possible strategy you can think of. At the same time, you would try to play a strategy that your friend cannot figure out. If you are successful in doing these two things, you will probably win more games than you lose. However, now imagine that your friend could mind read, so that your friend would always know which strategy you're playing. That means that if you play a pure strategy, your friend will always win. If you play rock, your friend will play paper. If you play paper, your friend will play scissors. If you play scissors, your friend will play rock. What should you do? You need to play a random strategy. A strategy where you yourself don't even know which move you're going to make next. For example, you could always pick two strategies and then flip a coin and pick one. However, if your friend also knows the probability for each move, then your friend still has an advantage over you. What could you do? In this case, you need to find a random strategy where your friend has no advantage even if he or she knows the probabilities. Now imagine that you and your friend can both mind read. That means that you know which strategy your friend is playing and your friend knows which strategy you are playing. So this means you both must play a random strategy. So let's say you read your friend's mind and now you know your friend's strategy. Then in response you adjust your probabilities for each move to be the best response to your friend's strategy. And then your friend knows your strategy, so your friend will adjust their probabilities to be best responses to your strategy, which then makes you adjust your probabilities again, which then makes your friends adjust again, and so on and so on. Now the question is, will this go on forever, or will you arrive at a stable equilibrium? For example, in rock, paper, scissors here, it is easy to see that if both you and your friend play each move with 1/3 probability, this will be a stable equilibrium. If you play each move with 1/3 probability, your friend has no way to take advantage of this knowledge. The same is true the other way around. If you know your friend is playing rock, paper, scissors each with 1/3 probability, you also have no way of taking advantage of this knowledge. So maybe the solution is to always play each move with the same probability? Let's consider a different game. By looking at the best responses, we can see that the game has no Nash equilibrium in pure strategies. Now let's say your friend plays left and right with the same probability, that means 50%. What should you do? In this case, you should always play up, because that gives you a higher expected utility. Why? Because if you play up, then with 50% probability you earn 5, and with 50% probability you earn 3. However, if you play down, you earn 0 with 50% probability and 4 with 50% probability, so down will have a lower expected payoff. However, if you always played up, then your friend should change their strategy and play always right instead. And if your friend always plays right, you should respond by always playing down. And if you're always playing down, your friend should respond by always playing left. To which you should respond by playing up. And so on and so on. So clearly this is not getting us anywhere. We need to make this more general. So let's say you play up with probability p and down with probability 1 minus p. And your friend plays left with probability q and right with probability 1 minus q. So here is the probability table. So the combination up left is played with probability p times q. The combination down right is played with probability 1 minus p times 1 minus q, and so on and so on. So even with these general variables, we can still calculate expected payoff. So your expected payoff will be the probability of up and left times the payoff you get from up and left, the probability of up and right times the payoff you get from up and right, the probability of down left times the payoff you get from down left, and the probability of down right times the payoff you get from down right. And this simplifies to 4 minus p minus 4q plus 6pq. And we can do exactly the same for your friend. Your friend's expected payoff will be 6p plus 3q minus 8pq. Okay, so here are the expected payoffs again. Now in a stable system, Knowing your friend's strategy does not make you adjust your strategy and vice versa. Otherwise, if you would still adjust, it would not be stable. So this means in a stable system, when you change P, so the probability of playing up, your expected payoff remains the same. Because if it does not remain the same, you do have an incentive to change your strategy. The same must be true for your friend. In the stable system, if your friend changes the probability of playing left, so Q, this should not have an effect on expected payoff. So this means that the slope of your expected payoff with respect to P and the slope of your friend's expected payoff with respect to Q must both be 0, because the slope of 0 means there is no change if you change this variable. So let's look at the slope of your expected payoff. So the slope is of course the derivative with respect to P, which is -1 plus 6Q, and this should equal 0, which solves to Q is 1 over 6. So this means if your friend plays left with probability 1 over 6, you have no incentive to change your probability of playing up. Now let's look at your friend's payoff. Now we take the derivative with respect to Q, and we get 3 minus 8P. Again, this needs to equal 0, and this solves to P equals 3 over 8. So if you play up with probability 3 over 8, your friend has no incentive to change the probability of playing left. So once more, when you play up with probability 3 over 8 and down with probability 5 over 8, and your friend plays left with probability 1 over 6 and right with probability 5 over 6, then the system is stable and nobody has an incentive to change their strategy. Now, how do we call a system when nobody has an incentive to change their strategy? Yes, that is called a Nash equilibrium, and in this case it is a Nash equilibrium in mixed strategies, because the strategies are not pure. So let's check our result. Your friend plays left with probability 1 over 6 and right with probability 5 over 6. So if you play up, your expected payoff is 1 over 6 times 5, the payoff you get from up left, plus 5 over 6 times 3, the payoff of up right. And that is 10 over 3. If you play down instead, your expected payoff is 1 over 6 times 0, the payoff of down left, plus 5 over 6 times 4, the payoff of down right, which again is also 10 over 3. Of course, the same is true for every combination of up and down, so indeed you have no incentives to change your probability of playing up. If you play up with probability 3 over 8 and down with probability 5 over 8, then if your friend plays left, the expected payoff is 3 over 8 times 1, the payoff of up left, plus 5 over 8 times 3, the payoff of down left, which is 9 over 4. And if your friend plays right, the expected payoff is 3 over 8 times 6, the payoff of up right, plus 5 over 8 times 0, the payoff of right down, which is also 9 over 4. So your friend has no incentive to change the probability of playing left. So indeed we have found a stable equilibrium. Importantly, here in equilibrium, both you and your friend are indifferent between playing each of your strategies. So this means we have found another, maybe a simpler way, to find a stable system, meaning the Nash equilibrium in mixed strategies. In the Nash equilibrium in mixed strategies, each player is indifferent between playing each of their non-dominated strategies. Because if they were not indifferent, they would play the one they prefer, obviously. So let's find the Nash equilibrium in mixed strategies for the game on the right. As we've just said, player 1 should be indifferent between playing up and down. So this means the expected payoff of up must equal the expected payoff of down, otherwise the player is not indifferent. The expected payoff of up is 2 times Q plus 3 times 1 minus Q. And the expected payoff of down is 1Q plus 4 times 1 minus Q. And if we solve the equation, we find that Q must equal 1/2. And at the same time, player 2 should be indifferent between playing left and right. So that means that the expected payoff of left must be equal to the expected payoff of right. The expected payoff of left is 6P plus 2 times 1 minus P equals 4P plus 8 times 1 minus P. The expected payoff of right. And that equation solves to P equals 3 over 4. So if player 1 plays up with probability 3 over 4 and down with probability 1 over 4, and player 2 plays probability left with 1/2 and probability right with 1/2, no player has an incentive to change their probabilities, and therefore we have a Nash equilibrium in mixed strategies. Now, does every normal form game have a Nash equilibrium in mixed strategies? If you think about it for a second, you should be able to answer this. The answer is of course no. We know that the prisoner's dilemma has one dominant strategy for each player, so these strategies are played with 100% probability, so there cannot be a mixed equilibrium. However, every finite game has at least one Nash equilibrium, either one in pure strategies or one in mixed strategies, or potentially both and potentially more than one. And that is by no means trivial. In fact, for a long time this was unknown until John Nash proved it and later received the Nobel Prize for this proof. This is also the reason why the equilibrium is called Nash equilibrium. By the way, you should know that an equilibrium counts as mixed strategy even if some players play pure strategies, as long as at least one player plays two or more strategies with some probability. Alright, before we end this video, one more example. So look at the game on the right. It should be familiar. What type of game is this? This is a Battle of the Sexes coordination game. Does this game have Nash equilibrium and pure strategies? The answer is of course yes. Up left and down right are both Nash equilibria. But we will see the game also has a Nash equilibrium in mixed strategies. So let's find it. Remember, player 1 should be indifferent between playing up and down. So the expected payoff of up should be equal to the expected payoff of down. The expected payoff of up is 5q plus 0, and the expected payoff of down is 0 plus 3 times 1 minus q. And that solves to q equals 3 over 8. And player 2 should be indifferent between playing left and right. So the expected payoff of left should be equal to the expected payoff of right. The expected payoff of left is 3p plus 0, and the expected payoff of right is 5 times 1 minus p plus 0. And that solves to p equals 5 over 8. So the mixed Nash equilibrium in this game is that player 1 plays up with probability 5 over 8 and down with probability 3 over 8, and player 2 plays left with probability 3 over 8 and right with probability 5 over 8. Of course, it is not a coincidence that the ratio of the probabilities, 3 to 5, equals the ratio of the payoffs here. Okay, so now you know how to find a Nash equilibrium in mixed strategies. Practice a bit and then try to solve the quiz.